ago, like most normal master students, and right away he wanted to work on polymorphism, and that's what he's here to talk about today. We're on this project on polymorphism. It was neat because he already had an idea. This is a guy who, in his earlier life, college student at Southeast Missouri State University, was a computer information systems major. Was that or computer science?
It was actually network administration.
Network administration. And just decided at some point, I want to do something substantive and substantial. And decided, I think biology is the way to go. Even targeted early on, he had some good advising there from a little bit from Dustin Siegel, but especially from John Davenport. And realized right away, I'm going to do something like good. He didn't mean good like, do a good job taking up, cleaning his house. I meant good like do something substantial that will stand as something that I added to society, but I should become a biologist and discover something. So that's what he's here to come and get trained to do. He is probably the oldest student I've ever had, and I don't mean that in age. Some of you know about Chris, and oh my God, he just, aside from a few slip-ups here and there, he's just an old man. See, you get what I'm talking about. I mean, how many of us would, he's actually not as old as you think. Dude owns a house, he's got a retirement portfolio, he pays attention to it, and look at all the faculty here. I know there's one somewhere, but we're probably not paying attention to it, So in that way, he's kind of like an old man. He's also like an old man in that he's learned a valuable skill set that takes many people a long time to develop, which is you give input, he takes it in, and he says, all right, I can do that, and I'll implement that. His expression for doing that action is he says, fair enough. The number of times he said, fair enough, to me and to other faculty since his arrival here is, you just can't count. And that shows that he's been open to learning stuff. I don't know if he's ever said that to anybody in this room, but he said it to me a lot of times. He says, fair enough, which means, I hear you, I'm going to learn to do that. So a few more comments about him saying fair enough. His initial project on polymorphism was to work on fabricated paedomorphism in the Louisiana newt. But the husbandry wasn't working out. It can be incredibly challenging, as other people in this room know, to say, I'm going to get adults against. That is really hard. There's very few amphibians and reptiles on our earth really predictable activity. And it's a big challenge. It's good to try that, but it wasn't working for Louisiana newt. And I said, well, I know a locality back in my own old place in North Dakota, and that's workable. You want to take a drive? And he goes, fair enough. And so we make this drive to North Dakota. And he says, yeah, let's do that. So we go there, and he'll tell you about that locality of it today. And it's kind of a remarkable locality. But my favorite thing about that field trip, it was a great field trip, by the way. That was a good field trip, wasn't it? It was a great, really good field trip in all ways. The best thing about the field trip was coming home. We finished our sampling on a Sunday morning, and I decided, we've got these animals, they're on ice, but they need to be alive when we get back here. And so I was a little stressed about that, plus I'm kind of a homebody, and I was sick and tired of being away from home. I mean, the second I drive away from home, I'm like sick and tired of not being at home. So I was like, well, let's go home, let's just drive. And he's like, you mean in one shot? I said, yeah, in one shot. It's a 29-hour drive from the field site to get back. Now that's okay. Everybody has a long drive story in their life. But this is kind of a good story because it shows you how he's an old man and probably older than everybody in the room. We're driving back, and at some point, we just get kind of punched. It's a long drive. We've hit about 21 or 22 hours in the drive. And we're at a gas station, and Chris says to me, hey, Beachy, can we just, my parents' house is literally 15 minutes from us. Can we just go there and sleep and drive home in the morning? And the morning was only like 4 or 5 hours away. And I was like, no, we got to get back. It's about the animals getting back. And he's like, yeah. And I told him, don't worry about it. I'm on it. I'm talking home. Drive. And Chris is very calm and says, fair enough. So he gets in the passenger side. I get behind the wheel. Right away, he's snoring right away. He's out. I get 5 minutes down the road, and I'm, Chris, you got to drive. You got to drive. He was so calm. He didn't give me the middle finger. He just said, fair enough. And he sat behind the driver's seat, and he drove us all the way home. and I slept almost the whole way. So he's a fine lad, he's an old man. I'm really excited that he decided to become a biologist. So now he's going to talk about biology. Chris.
All right. Well, thank you, Beachy, for that intro. Today I'm going to be talking about kind of what I've been doing for the last 2 years. That part has been understanding the life history of the Western Tiger Salamander. So this is going to be kind of our itinerary for this talk. We're going to start with some introductory materials, talk about heterochrony, talk about the natural history of my species, and then we're going to move to part 2, which is going to be kind of a summary of a laboratory growth study that we did. Then chapter 3 is going to be analysis of what kind of 2 separate life history databases. I'll talk about that more when we get there. And then part 4, we're going to take all the information from 2 and 3 and kind of put it together into some conclusions about life history biology. So let's start with heterochrony. So heterochrony is a change in the timing or rate of developmental events during ontogeny, and it generally results in one of 2 things, either paedomorphosis or paramorphosis. Examples of paedomorphosis and paramorphosis is the classic example of paedomorphosis is like the axolotl. We've all seen axolotls here, I'm sure. This is a tiger salamander. This is one of my specimens. And then the example of paramorphosis is like the Irish elk and their massive, overly developed antlers. So this figure kind of illustrates heterochrony. There's a lot here, so we're going to break it down. So on our x-axis, we have time during ontogeny. And there's essentially 3 different factors that can be manipulated to give you these heterochronic changes. You can change the onset by moving it either earlier or later, the offset by doing the same, or you can change the rate of development. So you can either accelerate it or decelerate the rate, like cell proliferation rates. So essentially, you get paedomorphosis. If you take your onset and your offset, if you shorten that developmental window, you'll get paedomorphosis. Any extension to that developmental time frame or an accelerated rate will give you a more paramorphic trait or feature or species, whatever you're looking at for your study. And for salamanders, that generally results in something that looks kind of like this. You can either have your traditional kind of biphasic salamander that has an aquatic life history, and then it goes through a metamorphosis and has a terrestrial life history, or you can have a paedomorphic species, and there's multiple different ways, either by changing the rate, the onset of development, offset of development, that can give you, this paedomorphic type of salamander. So I've said the word paedomorphosis a couple times, but I want to define it in the way that I use it when I'm referring to my species and salamanders that I work with. And that is, it's the retention of juvenile characteristics after reaching sexual maturation. And for ambystomatid salamanders, that looks like the retention of gills, or external gills for the most part, and then a flattened, kind of compressed, blade-like body that's good for moving through an aquatic environment. But then, within Caudata as a whole, there's kind of 2 different types of paedomorphosis that you see pretty commonly. There's facultative paedomorphosis and obligatory paedomorphosis. For obligatory paedomorphosis, it's required by their development. You will be paedomorphic regardless of environmental conditions, and that's things like hellbenders, siren, and puma, and the axolotl is an obligatory paedomorph. But facultative paedomorphosis is really where my interest lies, because these salamanders are capable of being paedomorphic, but they don't have to be paedomorphic. Examples of that is like a lot of the newts that I planned on working with in the beginning when I came here, and then a lot of species within the Ambystoma are facultatively paedomorphic salamanders. So this illustrates the life history of the Western Tiger Salamander. So they're laid in a larval aquatic environment as eggs. They hatch out into a larva. That larva grows and develops, and then it reaches a point where it can go either one of 2 ways. It can go this terrestrial route and go through the metamorphosis, become a terrestrial salamander, sexually mature sometime between metamorphosis and by the time it sexually reproduces for the first time. Or this larva can just remain in that aquatic environment, keep its same body plan, same body form, sexually mature in that aquatic environment. It can live out the rest of its life there if it chooses to do so. and then they can lay their eggs. But this paedomorph is, even once it has become paedomorphic, it can also go through with metamorphosis later in life if the conditions are right. So this is the range of what's commonly referred to as the tiger salamander complex. Essentially anything over here, anything west of the Missouri River, is Ambystoma mavortium, species that I've worked with, and anything east is Ambystoma tigerinum, the eastern tiger salamander. And I don't have to tell anyone in this room that the environment through this whole range in southern Canada is much more different than what it is down in Mexico. And we're going to talk a little bit about ecology in that. So on that nice 29-hour trip to North Dakota last year, I took these pictures standing at the banks of the ponds where we captured our salamanders from. This one here on the left is a very deep paddle pond. It's maybe up to 10 meters deep. The one on the right, it's more expansive, not quite as deep. But the real thing to note here is that these ponds are very eutrophic. We have these massive moss mats here. They're very large, and when you're standing on the banks of these ponds and you look down through that water column, you see lots of macroinvertebrates swimming around everything. There's lots of food here in these ponds for these salamanders to eat. But this is North Dakota. It gets pretty cold. Those ponds freeze over with ice. Snow gets put on top, and there's still salamanders underneath that ice there doing their salamander thing. So a week after I took these pictures, so it was about mid-July last year, I had the privilege to be at this location, which is a very different location, but these are ponds also full of the same species of tiger salamander. So I took these pictures at JMIH last year. A lot of us were there. You can see there's still snow here on the mountainside. It's melting. That ice-cold water's draining into this lake. That looks very different than the lake did in North Dakota. This is a very oligotrophic lake. We have this salamander walking around here. There we go. So there's not a lot of primary production going on. The trophic hierarchy isn't very complex in this lake, so that's an interesting distinction to make. So let's pick any random day and look at some temperature profiles. Why don't we look at today, right now at 8:09 Mountain Time in Alta Ski Resort. It's currently 66. High today is going to be 74. Right now in Minot, North Dakota, it is 73. High is going to be 85. So there's some fairly distinct temperature differences between the northern plains populations and salamanders that occur there, and then in the more montane regions. So we're going to come back to that idea again later, but I want to point out that in the northern Great Plains populations that I've worked with has been, the winters are very cold and harsh, but the summers are fairly warm. They occur at low elevation, very eutrophic lakes. And the montane populations of tiger salamanders, they have cold, harsh winters up there in the mountains, but the summers are rather mild. A lot of us were at Snowbird last year, and end of July, and it was absolutely beautiful weather. It maybe got up into the 70s when we were there. It was great. They occur at really high elevation, very oligotrophic lakes there as well. Not a lot of primary production going on. So that leads me in to the laboratory growth study, the chapter 2 of this talk, where my two main variables were temperature and food. So I feel like throughout the range, if you can understand how temperature and food influence the life history of this species, that you can really learn a lot about its life history. So for our high temperature treatment, the temperature was 23 degrees, low temperature was 15.5 degrees Celsius. We had essentially what was an ad libitum treatment and essentially a starvation treatment. We gave them just enough to get by, but not much more. So here's some cute salamander videos of them eating and doing things. There we go. I didn't expect them to eat those pellets at first. No, they're wild caught animals. Put them in the lab and fed pellets, but they ate them just fine, luckily enough. All right, so I had some hypotheses that I wanted to test with this 2x2 growth experiment. And the first one was, does the warmer water temperatures cause individuals to metamorphose earlier than cool temperatures. Next are the salamanders that grow rapidly will be delayed metamorphosis. And 3 are males more likely to express paedomorphosis than females. So here is some statistics. There's kind of a lot here, so we'll go through it piece by piece. So we have our univariate ANOVA statistics. Let's start there. So 3 different things that we measured was larval period. The experiment ran for 50 days, so started on day 0, ended on day 50. We have size, which is measured in snout vent length, which is from the tip of the nose to the posterior margin of the cloaca, and then growth, which was just final SVL minus the initial SVL. So for larval period, we see that temperature has a significant effect on the larval period, but interestingly, food did not have any effect on the larval period. The high and low food treatments didn't seem to impact their timing of metamorphosis. For size, we see that we successfully implemented our growth treatment. Salamander, there was a distinction between the size and the high and low temperature and food treatments, and the same goes for growth. And we see for all of these, for especially these 2, there's a food by temperature interaction here, but we don't see any significance in that interaction. So there's no additive effect. This one is near significance, but not quite. So we'll just skip on that for now. Let's talk about our MANOVA results. The input variables or the input data that went into that was larval period, SVL, and growth. And we see that food had a significant effect on those 3 variables, and so did temperature as well. So let's look at some figures. So here we have 2 different figures. One is a food treatment figure, and the next one is temperature. We see that our high food treatment salamanders that were given high food, that were given more food, grew more, not necessarily shocking. For our temperature, we see that salamanders in our high temperature treatments grew more than salamanders in the low temperature treatments. And then next on our y-axis, we have our larval period, and all of these bars represent standard error, by the way. But we have our larval period here. And this was something that became intuitively obvious rather early on in running this experiment, that salamanders in the high temperature treatments metamorphose significantly earlier, faster, and more often than salamanders in the low temperature treatments. And here we have a figure that on our x-axis we have larval period. So this is through time, and we have the percent metamorphose. So we have the percent of each of our 4 treatment groups through time, the percent that has metamorphosed through time. The filled-in circles, the black shapes, are the high temperature. Open shapes are the low temperature. Triangles are high food. Circles are low food. And this figure does a really good job of illustrating the effect that temperature had, but that food didn't have any impact on the larval period. So we see here that our high temperature treatment, they began with metamorphosis earlier. They also finished earlier, right about here, and all of them metamorphosed by the end. But for our low temperature treatment, they started later, and by the end, not even all of the salamanders in the low temperature treatment finished with metamorphosis. And here we have an XY scatter plot. With our x-axis, we have larval period, y-axis, we have growth, and we're looking at essentially four different figures here. These 2 over here are temperature, these 2 here are food. So let's start here with the left. We're going to go through all of them, but our temperature, high temperature, we see that we have the most positive relationship in our high temperature between larval period and growth. So these salamanders that are were in this treatment had the most positive relationship between larval period and growth. So each day that they were in this experiment, they grew more on average than the other treatments. For our low temperature here, you see that there's still a positive relationship between larval period and growth, but it's not quite as steep as a slope of that regression line as what it is there. We go to our food, we see that there is still a positive relationship between larval period and growth. But the interesting thing happens in our low food treatment. where it becomes a negative relationship between larval period and growth. And we see a lot of dots here that are below the zero. And it's kind of a common observation that when salamanders go through with metamorphosis, they can actually shrink. They're not being fed very well. They shrink the size between their snout and their vent length. So that's an observation made there, that there's a negative relationship between the larval period and growth if they're not being fed well. The next thing I wanted to look at is, so I had male salamanders, female salamanders. I also had immature and mature salamanders. So I wanted to see if there was any significance between, you know, those 4 different groups there. And we don't really need a p-value to tell us that 26 mature males and 0 mature females is a very significant value. So we see that, you know, there are so many more males. It was unexpected that I didn't have any mature females, but there are a lot of mature males, and we're gonna get back to that idea later. So let's get back to the hypotheses that we talked about at the beginning. So hypothesis 1 was that warmer water temperatures will cause individuals to metamorphose earlier than the salamanders at cooler temperatures, and our results support that idea. We saw that it became pretty clear early on that salamanders in the warmer temperature metamorphose way earlier, way more often than salamanders in cooler temperature treatments. Next, the salamanders that grow rapidly will metamorphose later than individuals that grow slowly. There's some optimization models that support that idea, but our results don't. We see that in our highest, in the treatments that had the highest growth, they also had the earliest rates of metamorphosis. And 3, that males are more likely to express paedomorphosis than females, and we had 26 mature males, 0 paedomorphic females. So our results support that idea. All right. So now we're going to move on to part 3, which is the analysis of kind of 2 separate life history databases. The first one was life history database built by the Amphibian Growth Project a long time ago. It's been available on the internet for 10 years and no one's ever done anything with it. So I had the honor of doing that. But there's over 2,400 specimens logged into that database and over 10 years of data. Some of the specimens that BT's worked with in the past were preserved, put into jars, and have sat in the lab for a long time. So I decided to open up those jars. Me and Juan opened up those jars and measured salamanders for what seemed like days. But we have 340 specimens there, and they were collected from all over North Dakota. The questions that we asked of this database are a little bit different than the questions we asked of those preserved jarred specimens. So let's talk about that. So they were collected in several different ways, whether that be drift fence, where the salamanders are wandering along trying to get to the pond. They ran into this wall and then end up falling into a bucket, by seine hauls, or by minnow traps. So we had just some kind of natural history observations that we wanted to get at some questions. One being, what's the average size of metamorphosis in nature? We have 2,400, over 2,400 data points. We think we can answer that question. What's the minimum size required for sexual maturation? We have a lot of data. Again, I think we can get at that. But then as far as hypothesis testing goes, we wanted to see if males are more likely to express paedomorphosis than females. That's a trend that we saw in the laboratory growth study, but is that true in nature and true in this database, or was it artificially created? And then second, will the Northern Plains populations obey Whiteman's dimorph-pedomorph model? No, I haven't covered that, so we will now. So this is Whiteman's dimorph-pedomorph model. Howard Whiteman published a paper, The Evolution of Pedomorphosis, in 1994, that had a figure that looks similar to this. So we're going to go through so I can explain this. But that paper, Whiteman 1994, was really kind of a keystone paper in me deciding to carry out this thesis project because I really like the idea of this model. But on our x-axis, we have body size, y-axis, we have the number of individuals in a given population. And there's essentially 2 different hypotheses posited by this model. There's one, the best of a bad lot hypothesis, and the pedomorph advantage hypothesis. So we'll start with what this R is. So R is representative of the minimum body size required for sexual maturation. M is the minimum body size required for metamorphosis, and P is the minimum body size required to be, it's a hypothetical number, but it's the minimum body size required to be paedomorphic via the paedomorphic advantage hypothesis. So let's first talk about salamanders that fall in this paedomorphic range here, this best of a bad lot hypothesis salamanders. So essentially the argument here is that these salamanders, they have a pretty small body size. They're not doing exceptionally well in this population, but they have attained body size greater than R. So they can sexually mature their gonads and they can potentially reproduce, but they haven't attained a body size larger than M, so they can't go through with metamorphosis. So any salamander in this range, the argument is that they should sexually mature their gonads, make the best of a bad situation, and try to mature and reproduce at least once in their life and at least early. Any salamanders that fall in this biphasic range here, those are salamanders that have the traditional kind of biphasic life history where they start out in the aquatic environment, they go through with a metamorphosis and have a terrestrial life history. And then the paedomorphic advantage hypothesis here. So salamanders that fall in this paedomorphic range are salamanders. These individuals have attained a really large body size. They're very large compared to everyone else in the population. They're doing really well. So the argument for this is essentially these salamanders are doing so well. If you're a facultatively paedomorphic salamander, that means you can be paedomorphic. You don't have to leave that aquatic environment. You're doing really well in it. So rather than going through with metamorphosis and moving to an environment that might be potentially detrimental or more harsh to whatever individual might be in this situation, just stay in this aquatic environment, sexually mature there, and then later if things get bad, you can then leave at that point. So we're going to get back to that later. We're going to test that model and see if it holds up for our populations. But for now, let's get to some of those natural history observation type of questions. So this is tiger salamanders during what we call the metamorphic season. So this is late July through early September. And here we have two different figures, two different size frequency histograms. And here this transforming group. So let's talk about that real fast. So larval salamanders have these big fluffy gills. Once they go through with metamorphosis, they go away. Somewhere in the middle, they have gill nubs. So if they have gill nubs, they were classified as transforming animals. And when we looked at the big database that had been built, we see that we had 363, so a fairly large sample size of salamanders. And we see that they had an average SBL of around 90 and a half millimeters SBL, which is a pretty large salamander. I have jars of salamanders up here. If you want to look at them at the end, all of these salamanders are fairly big. Ambystoma mavortium is actually the largest terrestrial salamander. But so we have, an average size of metamorphosis there, about 90 millimeters SBL. The second figure has kind of two clear size classes on it. We have this size class here, these black bars, that essentially mimic the size class there. And chances are these are young of the year individuals that have been growing. And any individual here that given another day would have fully resorbed those gills, and they would have been here in this box. But we also see a second size class. These individuals up here at about 117 millimeters SBL are quite a bit larger than the rest of our size classes here. So these salamanders that are on this size range, they're one of two things. One, they're former paedomorphs. Maybe they've been in these ponds hanging out for the last 2, 3, 4, 5 years, however many, and are just now, for some reason, deciding to go through metamorphosis and moving to a terrestrial environment. But actually, an observation made of this systematic population is an observation that really hasn't been made of any other population that we know of. Most abystomad salamanders lay their eggs in ephemeral pools. We have permanent ponds that we were working with. So an observation that's been made is that when the terrestrial salamanders come from the land to the water to breed in the spring, they do their breeding, their mating, their courtship stuff, and then a lot of salamanders, they leave, they go back to the land. But an observation that's been made is that a lot of salamanders in this population, terrestrial salamanders, when they come to breed, they stay for the summer. They stay and hang out in this pond, and they eat throughout the summer. That's was seen by a bunch of same holes towards the later end of the summer that had fully transformed animals caught in the same that had no other reason to be there. So that's an interesting group there and an interesting observation. So now I'm going to talk about kind of those preserved specimens, so part 2, that second database that was built. So me and Juan went and cut open what seemed like 1 million salamanders. There's all those jars. That's that jar. There's so many of them, but we cut open and there was 340 of them. So now we're going to talk about those 340 specimens. So the data that we took was snout vent length, so their size, and we see that there's a significant difference between the sizes and the life history status, size and sex, size and maturation status, and then an interesting interaction between the sizes and the life history status and maturation status. And we're going to talk a lot about that here coming up. But I want to make it clear that this can get pretty sloppy pretty quickly. It's a complex system that we're working with. Because any random tiger salamander that you pull out of the wild, or that you pull out of that jar, it's a tiger salamander. But then it's either larval, transforming, or transformed. And then within that, it's either sexually mature, sexually immature, and then within that, it's either male or female. So we have 12 different groups to work with. So what we're going to do now is we're going to take these 12 groups and we're going to put them into a chi-square analysis to see if there's any differences between these groups. So there's a lot here. So let's start. So here's our larval group, here's our transforming group, and our metamorphs group. We'll start with just our end values. We have 199 larval form tiger salamanders, 31 transforming salamanders, and 110 fully metamorphosed salamanders. So we also have our females and males and our immature and our mature column. So these numbers at the top of each box is 50, 34, 26. Those are the observed values. So of those 340 salamanders, we had 50 larval immature males, and we had 34 metamorphic mature females. The numbers in the brackets are the expected numbers of the chi-square analysis that it expects to see, and then the numbers in the brackets is the chi-square value. So this 5.4, so this box here contributes 5.01 to this 11.98 value. So the higher this number, the more significantly different your observed value is from the expected value. So I'm going to speak for 2 of these categories for both larval and metamorphs at the same time, because we see the same trend in both those boxes. That's being that we see more mature males than the expected values. We see less immature males, less mature females, and more immature females for both larval and metamorphs. So that seems to hold through. For our transforming group, we had a relatively small sample size, and we don't see any significant trends there. But there is significance in our metamorphs and our larval groups. All right. So this is a relatively big figure, and we're going to go piece by piece here. So it's a size frequency histogram. Anything above that line is females. Anything below that line are males. All right, so here is our immature larval females and immature larval males. We initially see a sex bias there. Next, we're going to go to our mature larval females and males. So these are the paedomorphic salamanders, these black bars. Next, we're going to do our immature transforming females and males. It's not a big sample size there. For our mature, we're going to go mature transforming females and males. Same thing. For our immature metamorphosed females and our immature metamorphosed males. And then for our mature metamorphosed females and males. So at the end, that's kind of sloppy and it's hard to interpret. It's fair enough. So we're going to look at the same figure a couple different ways in these next slides. So here we just have our male tiger salamander. So anything that was below that line is now represented on here. Here we have our immature column, our mature column, our larval, metamorphs, and transformer. So same thing, size, frequency, histogram. And if you stare at this long enough, there's a lot to be gathered from this, but I'm going to pick out just a couple things and kind of harp on them for a second. So for this box here, so our immature larval male tiger salamanders, we see that their size is everywhere. They're really small, they're really big, and they're everywhere in the middle. But if we want to ask a question about maturation, we should look at this column over here. So let's compare our larval mature male tiger salamanders and our metamorphic male tiger salamanders. Let's compare their maturation. So we see that they can get rather large, but that minimum size of maturation between the larval form and the fully metamorphic form is interesting. And it's a trend that we also see in the females as well. So the smallest size here for larva is right around, it's like about 95 millimeters SBL. And for the metamorphs, it's at right around 85 millimeters SBL. So it's significantly smaller. And we have a pretty large sample size. So what's going on there? And if we look at our females, we see this exact same things. We see a size range of the immature females. They're small, they're big, and they're everywhere in the middle. But it's that same minimum size of sexual maturation that's interesting. So for our paedomorphic females here, we see a relatively large, over 100 millimeters SBL size required for sexual maturation. But in the metamorphic form, so if they go through metamorphosis, it's significantly smaller. So it's an interesting observation. Let's move on for now. So the real reason this figure is here is not necessarily because I'm going to talk much about it specifically, but I want to explain why I decided to use violin plots. So violin plots are really good at visualizing bimodally distributed data. So we see here in our immature males that there's a small distribution down here, and there's a large distribution down here. These can essentially be read as vertically based, as like frequency histogram. So there's a small group here, there's a larger group here. But we see that same trend of males maturing at a smaller size, females maturing at a larger size. But let's talk about some of our questions that we talked about at the beginning. So what's the average size of metamorphosis in nature? It seems like it's around 86 to 90 millimeters SBL. It's an interesting natural history observation to make. And then what's the minimum size required for sexual maturation? This one got kind of complicated. So for larval males, it's right about 96 millimeters SBL. For metamorphosed males, it's right about 86 millimeters SBL. There's a fairly large distinction there. For larval females, it's 104 millimeters, and for metamorphosed females, it's 93 millimeters. So this was something that I didn't expect to see. It's not something in the database that I really was searching for, but once I got looking at the data, this became maybe one of the most interesting trends is that sexual maturation, if you're going to be paedomorphic, you have to be larger. So our paedomorphs are larger, but if you're going to be metamorphic, you can mature at a smaller size, which is interesting. So for hypothesis testing, males are more likely to express paedomorphosis than females. What did our results say about that? If we think back to that chi-square table, our results support that. We had more mature males, less mature females, paedomorphic males and females. So our results support that idea. And next, our hypothesis 2, the thing that I really wanted to get at with this thesis was testing the best of a bad lot in the paedomorphic advantage hypothesis. So remember, we have our paedomorphic advantage hypothesis where we have large paedomorphs and small paedomorphs. So what does this say? Our results is it's complicated. So I'm glad I was able to get at that so well, right? But let's talk more about it. Let's skip to our conclusions. And we're going to talk about why it's complicated and really kind of dig into it there. So this is Wyman's dimorph paedomorph model. Again, we have our large paedomorphs and our small paedomorphs. when we compare that to the sizes of our mature larval salamanders, our paedomorphic salamanders, this group here, we see that when we look at this violin plot, which is good at visualizing bimodally distributed data, we don't see a bimodal distribution here. We just see a large size class. We move this over, we just see a size class that is attained to a very large body size. So, for Whiteman's paedomorphic bandage hypothesis, so the large paedomorphs, our results support that idea. But for the best of a bad lot hypothesis, of our 340 specimens, we didn't have a single sexually mature, smaller size class of salamanders. So our results reject that idea. But that's complicated. And unfortunate. It's not unfortunate. It's very, very cool. But in 2012, Whiteman wrote, most of the paedomorphs at our study site were produced through a best of a bad lot mechanism. So we have to ask, what's going on? Why didn't we see that too? Why didn't our results, why didn't my results support that same conclusion? Why does he have a bunch of small paedomorphic salamanders and I only have big paedomorphic salamanders? Well, it wasn't intuitively clear at the beginning of this, but now that we've reached the end, I think it is the differences between the populations that Howard Whiteman works with. He works in Mexican Cut, Colorado. It's a high altitude montane population. They have a cooler temperature, a shorter growing season there. They have a slower metabolic rate because of the temperature. For food, they have less primary production. The trophic hierarchy is less complex. Any macroinvertebrates that do occur in his farms, there's lots of competition for those macroinvertebrates. But for the northern Great Plains populations that I work with, we see that we have generally warmer temperatures. The growing season is longer. It's warmer for longer in the northern plains, which results in a higher metabolic rate. And then for food, there's more primary production. The trophic hierarchy is more complex, and there's an abundance of macroinvertebrates in those ponds like that I've worked with. So let's talk about some concluding thoughts. If I had to say like one sentence from each chapter that I feel like is the most important thing to pull from each chapter that can really be your take home of all of this, is that temperature near the end of the metamorphic season plays the primary role in quote decision to metamorphose and overwinter. But interestingly enough, food does not. Food did not affect our larval period at all in our chapter 2. In our part 3, minimum size of maturation differs not only between the sexes, which is kind of interesting, but also between the life history stages within the sex, which is a really interesting and very cool and very important observation to make. I guess as a kind of last thing here, we see that environmental differences between the montane and the plain populations, I think, is really the true thing that's driving the discrepancies that we see in Whiteman's model when he looks at his populations and we look at ours. Next, I think this is a classic case of ecology regulating development, ultimately producing similar morphologies but through different means to achieve a similar goal, and that goal is sexual maturation. So this is almost my last slide. There's kind of one or two more things that I want to say. One is that I did a bunch of work that never really quite came out the way that I wanted it to because of multiple reasons. That skeletal chronology, one of the things that I really wanted to get at was I wanted to put an age and a size at sexual maturation, so I could talk a lot about selection. Unfortunately, I couldn't get the methodology working properly, and then there was a massive pandemic, so I had limited access to the lab. I think we're close on that. I think it's more time. If I had a little bit more time, but that could become a fruitful part of this research. And I have to say, if there's any future directions, it would be to somehow get an age at sexual maturation. I think that would be a very fruitful exercise to really learn more about the life history of the Western Tiger Salamander. And with that, I have a lot of people to thank. First and foremost, Dr. Beachy for his support and guidance through this whole thing, as well for driving some of those 29 hours. And all my committee members, my project at the beginning, was quite a bit different than what it ended up being. So thanks for working with me through those changes and those difficulties. Thanks to Florence for teaching me skeletal phrenology. We're close on it. I think we'll get it working. Oliver for watching my salamanders while I was out of town. He did a lot of work that week. Juan for helping me measure what seemed like 1 million salamanders. All the BGSO graduate students being excellent friends and companions. You all have been wonderful. Also my dog. Thank you to my dog Brady. Next, for funding, the Edward G. Schleider Professorship, for funding a lot of this research. William and Alice Callaway Scholarship for funding me. Shana Forrester and Jay Fisher at the North Dakota North Central Research Extension for letting us go and trap salamanders there. And then the Bone Break Hospitality Research Center, which is kind of facetious. It's not a research center. It's just some really nice people in North Dakota that let me and Beachy crash in their basement when we were at their trapping. And then maybe most anyone who's worked for the Amphibian Growth Project through the years, they collected a lot of that data. I just have the pleasure of analyzing it here at the end. But with that, I'll take any questions.
Okay, we'll start with the in-room questions, and then as people out in internet land can begin asking their questions by using the text feature on the computer to send those in to us. So we'll begin with the in-room. Any questions for Ken?
Yes.
First set of experiments, it was all in the lab, right?
Yes.
You know, I have the pieces all together and a lot of stuff are in the out.
Yeah.
And you had this one result where all the males basically metamorphed into females.
Yeah.
Do I remember that?
Mm-hmm.
And then
Well, I had more mature males. Almost every individual except for 9 went through metamorphosis. I had more mature males. I had 26 mature males, 0 mature females.
and you said you were going to see what that looks like in nature.
Mm-hmm. Yes.
I
So
lost where that was.
okay.
I never found it when you were going through it.
That was the chi-square table. So let me go back to that.
Yeah, I remember the chi-square table, and that's where I thought I was going to be seeing it.
Okay.
Back.
So all of these salamanders were caught in nature and put in jars of ethanol. So I'm considering this nature.
Okay.
And we see this trend that there's more paedomorphic males here than what the chi-square
I can't
analysis.
see where your pointer's pointing.
50, there's that 34
Okay.
up there. So that was our observed value. In the chi-square analysis, expected there to be 23. And with females, we see that our observed value was 21 in the chi-square analysis. So if there's no biology going on, the chi-square analysis would expect there to be, 30, 32 salamanders. So based upon that, we see that paedomorphosis is more common in males. Males more likely to be paedomorphic than females.
So then this is the same result as the lab one.
Yeah. Yeah.
Now here's my real question.
Okay.
Can you explain that in some kind of evolutionary context?
Yeah, so I think it goes back to the energetics of producing sperm and egg. I think it's much more easy to produce a small sperm than what it is to produce, the hundreds of eggs that Tiger salamanders make. So I think that a lot of it has to do with that, is why we see that discrepancy there. Also, males very well could fertilize more than one female. So then these are going to mature as more fitness advantages, especially if they mature earlier. So I guess that's my reason for that.
Do you transform males reproduce with non-transformed mature females?
Yeah, that is observed. Yeah. Yep. Yes, T.
Okay, so you have the comparison between white and waffles. You have high elevation, cold growing,
Yeah.
So then there's your one like tropical amazing. Every grow, everybody eats every other time.
Sure. Yeah.
So you have this comparison between these two. What do you think is the sort of life history mechanism that links those two kinds of populations together. When you think of anything, especially based on your capture.
What do you mean by life history mechanism?
So why don't you mature when you're tiny? And you haven't grown very much. You grow maybe slowly. And you grow big, like you have to get over that hump of the rest of that lot.
Yeah.
We have that sort of valley, the uncanny valley in the middle. How do you go through that valley?
So I mean, whenever you have the smaller paedomorphs, the smaller vessel of fat lot, I mean, those individuals, they can't go through with metamorphosis. They don't have the body size. They haven't attained the body size to do it. So those individuals, in a way, are forced to be paedomorphic. So they don't have any option. But whenever you have salamanders that live in our nice exotic environment, lots of food, everyone's barbecuing, you mostly attain a large body size because it's easy to do so. And any salamanders that fall somewhere in the middle, they go through metamorphosis and become terrestrial. But yeah, I think that it comes down to those environmental conditions of those individuals. It's easy to attain a large body size in the more northern plains populations than what it is to attain a larger body size in those original plains.
So you have populations that are forced to be paedomorphic and populations that get to be paedomorphic.
Yeah, kind of in a way, yeah.
So does a reproductively mature paedomorph have to be rare within the population to be successful?
Does a reproductively mature paedomorph have to be rare to be successful?
In your just kind of tally up the numbers in the time frame, your reproductively mature paedomorphs are really rare relative to the adult forms.
Sure.
But that to be maintained in the population would actually have to be really rare to be important to be a successful strategy.
I doubt that it has to be rare. I wouldn't expect it to have to be rare to be successful. Yeah, I'm not sure that it would have to be rare. I guess that's fine. Whenever it occurs, I think it is successful basically every time. Because there's not a lot, the only predators in these ponds are other salamanders. And cannibalism is common, but it really hasn't been observed, especially in the northern plains populations.
Why don't you check your computer and see if there's some questions there?
Okay.
Right.
I'm not sure what happened to our projector either.
I'll take care of that. See if there's questions for me.
Okay.
Internet audience.
Okay, let's see. Are there any questions? I have. Great job. Great job. Love the picture of Brady. Congratulations. Nice work. That's what I got so far. Yeah.
Other questions from the room?
So I don't have more of a comment than a question because I like the way you do the Brian's question about the cost of eggs versus sperm. But when you were giving your talk, you expressed surprise that the females became mature at larger sizes than the males become mature.
Mm-hmm.
And I think you should not express surprise at that in this case for the exact reason that you just said. Right.
Yeah, that's fair. I guess the surprise lied in that there was difference between the life history stages and the size, rather than just the females attaining the larger size. That was something that I didn't really expect to see at all.
So say that again, we're not.
So there was a difference. I think the surprising thing was that, is this back yet? Yeah. I think the really surprising thing is that, one of the differences lies in their life history stage. So larval females are a lot larger, and the metamorphosed females are a lot smaller. I expected, there to be a single size maturation regardless of, you know, the life history status. So I think that is the surprising thing, is that there's a difference in sizes required for maturation based on the life history status. And for males and females.
So you mentioned that sometimes they go smaller than metamorphosis. How much is that? Couple of millimeters or maybe not?
Yeah,
Also,
yeah, it's not a lot. It's just a couple of millimeters typically when we go through metamorphosis. It's that we think it's the intervertebral distance when we go through metamorphosis. It shrunk a little bit. It's typically not incredibly drastic, but it does happen. Yes.
How often do you use? Do they have some questions in there? Multiple files?
In a single season?
Yeah.
Yeah, so they lay their eggs either singly or in small packets. So they reproduce, they oviposit, probably hundreds of times in a season. So, yeah, a lot.
You mentioned for like the paedomorphs versus the metamorphs.
I think some research has been done that does suggest that paedomorphs do have a higher fitness. But then again, that's been done with other Ambystoma salamanders, not this species. But it's hard to say if those paedomorphs were not paedomorphs, paedomorph advantage paedomorphs. So it gets complex. Yeah.
And so going along with that, white ones does that a lot more because they have much smaller sizes than you have. Or
Yeah, if we look at his data, on average, the salamanders are smaller in general
so
than salamanders in that yard.
That would be really interesting to see if the minimum size of sexual maturation is smaller than his population versus the that one.
Yeah, they would really complete that picture. Yeah. Yeah, I agree. I'll see if I can dig up some of this data. Is there any questions?
There's no questions from here. Any other questions from the room? All right, let's thank Chris one more time. We'll get a few minutes, and then the committee will stay here with you.
Okay, sounds good.
Nice job.
Thank you. Stressing all around. Glad I can shut that down.
That'd be great. You guys.
Thanks, guys. All right, anybody here? I'm gonna shut down this. Thanks for hanging out.